All right. Well, good morning and happy Friday. Hope you're all having, I guess, a good week. And just a friendly reminder: it's Mother's Day this weekend. So, I hope you have good relationships with your mom, and yeah, I think she would appreciate at least a phone call to say hello. All right. Let's take a look at today's lecture. And then just to allay your concerns and your fears, these are just applications of the naive Bayes classifier, which is a very kind of handy and helpful tool that we have. And you don't have to worry about these specific applications appearing on the midterm exam, okay? So you should know up to, I guess, Wednesday's lecture about naive Bayes classifier as kind of, the concepts and how that works. But as far as these specific examples, you don't have to worry about it for the midterm. But I did want to kind of show a couple examples where we can use the naive Bayes classifier, as a way to, perform some classification. And we use the naive Bayes classifier because we don't have to worry about covariance between these, whatever you call it, the kind of the input features. Okay, so one example is a document classifier. And so document classification is basically given this text, can we, categorize it, right? Is this article about politics? Is this article about sports? Is this article about health? Things like that, okay? And so these, you can have some kind of, automatic classifier. And the key here is that the inputs are going to be the words that appear in the document, okay? And we're going to have to take those words and basically make them numeric, and we're going to do that by just counting the words. But those will be our input variables, which words appear, and trying to estimate covariances between words is a really challenging task. And so the naive Bayes classifier says, you know what, just forget that bit, okay? Don't bother estimating covariances between words. We're going to just assume each word appears independently, okay, according to the probability distribution for that document class, okay? So, in reality, if certain words appear in the document, other words are also more likely to appear. So, for example, if the word senator appears in your document, then Congress is also more likely to appear, and maybe president and maybe government, right? And that's probably going to be a document about politics. And if you see the word baseball in your document, then probably team and player will also be a little bit more likely. So, we imagine there are covariances between words, but as far as document classification goes, the input space is huge, right? You might have, 50,000 words in your vocabulary, and now you have to estimate covariances between all 50,000 words, okay? And we can't just say, there's going to be covariance between these words, but you have to kind of, I guess, take all of the written language and try to estimate covariances between them. And sure, maybe huge large language models have some kind of thing in there, as part of their billions of parameters, maybe. But we're going to just keep it simple, and we're just going to say, you know what, let's not worry about the covariances, okay? We'll just say, hey, if there's an article and it's about sports, then team will be probably a little bit more likely. Player might be a little bit more likely. If there's an article about politics, then words like senator will be a little bit more likely. Words like president and law and Congress, those words might be a little bit more likely, but we're not going to worry about the covariances, okay? So the assumption, not likely, is almost certainly to be wrong. It simplifies, it really simplifies the model, and it still has good performance. And again, in machine learning, we really just care about performance and we don't worry so much about the assumptions. I don't know, maybe that's not the best strategy, but anyway. Okay, so a simple way to what we call vectorize our input for a document is the bag of words model, okay? There's a whole kind of subfield of natural language processing, and it's like this idea of how do you go from the words into the numbers, right? Because all of our matrices, all of our neural networks, what they handle are numbers, and so those are called vectorizers. And there's all kinds of different vectorizing models out there, and so if you play around with, there's a lot of like open source large language models if you're like interested in playing around, and so Meta offers their open source, basically AI tools and stuff. And anyway, they have different vectorizing things, okay? One of the simplest, and it's not a good one, but it's a very simple one that's easy for us to understand, is the bag of words model, okay? And basically, we just treat a document as a collection of words, ignoring word order. So you can imagine kind of like a cartoon where, I don't know. So imagine, there's a cartoon where somebody has like a letter or has a piece of paper, and then, like in the cartoon, they shake the paper and then the words just fall down, okay? And it's kind of like that, right? So you just have a collection of words at the bottom. The order doesn't matter. It's, and we call it a bag because items in a bag are unordered, right? If you have a backpack and I say, give me the third object in your backpack, it's a confusing question because you say, well, which one's my first and second and third object in the backpack? There's no order. So there's some major limitations in that here I have two documents, and these two documents have completely opposite meanings, right? This document says, it is bad, it is not good, right? Maybe we're talking about a movie or something, okay? And then someone else, their document, okay, and these are about as simple as documents as you can have. This one says, it is good, it is not bad, okay? But when you do the bag of words model, you just take the words and you say, how many times did these words appear, right? And so you get it appears twice, is appears twice, bad appears once, not appears once, good appears once. And it's gonna, like, the word counts for document 1 is exactly the same as the word counts for document 2. And so the bag of words model is going to treat these two documents as exactly the same, okay? It cannot distinguish the different meanings between these two documents just because basically the vectorized version, once you take the words and you turn it into a bag of words model, it's going to be exactly the same. So a popular topic in natural language processing is sentiment analysis, which is kind of like, somebody wrote a review, and is it a positive review? Is it a negative review? Are they saying good things about, they made a post on some social media site and they mentioned a celebrity. Are they saying something positive or negative about the person? So my personal opinion is if you're going to use a bag, don't use a bag of words model for sentiment analysis because, you're going to run into this problem where you're going to have two opposite sentiments and it can't tell the difference between the two, okay? The word not is really important, okay? As far as, sentiment analysis goes. However, when it comes to hey, is this document about politics or is this document about sports or whatever, then the word not is not as important, and you can just kind of look for keywords and just say like, oh yeah, you know what, we're seeing the words senator and Congress and representative like showing up a lot, so we're pretty highly confident that it's going to be about politics or something like that. Okay, but anyway, we're just going to go ahead and use the bag of words model because it's about as simple of a vectorizer that we can have. Okay, the naive Bayes classifier, for it to work and for you to be able to classify documents, requires a lexicon, okay, or a vocabulary that stores the estimated probability of each word appearing in a document that belongs to a specific class, okay? And so this is an extremely, extremely simplified version of a lexicon, okay? A real lexicon probably has 10,000, 20,000, 50,000 words, okay? Unique, we might call them tokens, okay? And basically, it's like the entire dictionary of the English language almost. And each word is going to have a probability associated with it, okay? For that document. And it'll be something, you know, basically like if the document is about politics, then, you know, compared to just the general baseline, all like no classification, the average, you know, if it's about politics, then, you know, senator, Congress, those words will have higher probabilities. If it's about sports, you know, team, player, you know, game, whatever, those will have higher probabilities. Okay, here I've chosen, these are just silly categories, but we can imagine a document or a sentence being about a fairy tale, or a document or sentence being about the game chess. Okay, and both chess and fairy tale often involve a king or a queen, okay? Maybe a knight, okay? But then other words will be kind of a little bit more unique, right? So here I say, so if you look at the word king, you know, in fairy tale, sometimes they talk about kings, and in chess, they certainly talk about the king. And for fairy tales, they talk about a queen, and chess will also talk about the queen. But as far as a princess goes, that's much more likely to, you know, as far as the fairy tale probability, it will have a high probability in fairy tale. But then regarding chess, you know, chess will probably almost never mention a princess, okay? And here, this is, again, a greatly exaggerated vector because I only have 8 words in my vocabulary. Knight might appear in both fairy tales and chess. Okay, the word rook, you know, appears in chess, but not probably not in fairy tales. I don't know. So I put a low probability there. Good might be a word in fairy tales, but also it could be a word in chess, like if you're talking about a good move or something like that, a good play. But then evil, you know, that could appear in fairy tales. For me, it's hard to imagine talking about evil while talking about chess. And then, you know, if you're talking about the board, okay, probably not so much in fairy tales, but likely in chess, okay? And, you know, the key here is that the sum of all of these words, probabilities, would add up to 1, okay? And the sum for, you know, if you take the column, it adds up to 1. So this is kind of our lexicon. You know, here I only have 8 unique words, which, again, a real one probably has 10,000, and because you have 10,000, your probabilities are also really small, like on the order of 10 to the minus 4, 10 to the minus 5, 10 to the minus 3, or things like that, okay? This I just kind of made up, but in general, you would actually train the lexicon by taking documents where you know the class, right? So you might say, okay, here's our archive of documents, and all of these documents have been labeled, okay? And then you would build up your lexicon, and so you would take your document and basically turn it into words, individual words or tokens, basically, you know, kind of using your bag of words model, and then you would, you know, kind of strip all of these things, like strip the punctuation, make everything lowercase, and then you would remove like what we call the stop words that don't really give us any information about class, okay? And then for each class, you say, okay, so here are all the documents about politics, and we've turned them into these tokenized words, and we've cleaned it up. We're just going to start counting. Okay, this document about politics, we see the word Washington. We're going to add a count to 1. We're going to see, and they're talking about, I don't know, this a house and so on and so forth. Okay, you just count all of them up, and then you divide by the total number of words that appeared, and you get a probability estimate. Okay, so a lot depends on the training data that comes in. Okay, so if you use like historical information, you might have documents about like Obama and things like that, and then probably words in today's documents about politics, probably Obama will not be mentioned as much, but maybe like Trump and Biden and things like that will be mentioned more often. And so depending on your training data, your lexicons might be outdated or old, but hopefully they still kind of work well. Okay, so here is just a very simple example. Let's say our document says this, right? The evil queen sent the evil knight to capture the princess. Okay, so based on this, if you had to guess, is this from a chess or a fairy tale? Okay, and there's a few things where it's like, okay, they're talking about a princess, so probably not chess. Okay, and they're talking about the evil queen and the evil knight, probably not going to be about chess either, right? So we're going to just ignore the words that aren't in our vocabulary, okay? And if we count the words that are in our vocabulary, we have the word queen appears once, princess appears once, knight appears once, and evil appears twice, okay? So we got, these are our words, and so now we'll calculate our likelihoods, okay? And so the likelihood is what's the probability of our data given the class. So we're going to say, okay, what's the probability of getting queen if it's a fairy tale? And so we have 0.2, okay? And then princess given a fairy tale, we have 0.25. Knight given fairy tale is 0.2, and evil given fairy tale is 0.11 each. So we have queen, princess, knight, and then evil. Evil appeared twice. We have our word count there is 2 for that, so we're going to do 0.11 squared. And this is our likelihood for the words that appeared. So we have 0.000121, okay? We can do the same thing, and we can say, what is the likelihood of our data if our document is chess, okay? So again, we have queen appears once, princess appears once, knight appears once, and evil appears twice. So if we look at our, okay, queen has probability 0.2, princess 0.01, knight 0.15, and evil 0.01. So when you put those in, 0.2, 0.01, 0.15, and 0.01 squared, and you get 3 times 10 to the minus 8. All right, so just comparing likelihoods, we have 0.000121, so 10 to the minus 4, and over here we have 3 times 10 to the minus 8, okay? So the likelihood for of getting our data under the fairy tale class is much, much, much higher than the likelihood of getting our data if it was a chess document. And so, for a true Bayes classifier, a naive Bayes classifier, we would, multiply it by the prior probabilities, calculate the marginal probability, and then calculate our posteriors. But I mean, just even kind of this, even without considering the prior probabilities, the fairy tale likelihood is order of magnitudes larger, and so when we classify it, we're going to classify as much more highly probable that it is a fairy tale document, okay? And so, yeah, in practice, the naive Bayes classifiers also multiply by the class priors, and so, if we knew 70% of documents are fairy tales at 30% chess or something, we can do that, put in our marginal probabilities, okay? Just a couple other things regarding document classification or naive-based classifiers is that during, there's something called Laplace smoothing, and sometimes as you're training your vocabulary, certain words might have a count of 0, okay? So, I don't know, you've got this lexicon of, 50,000 words, and, despite your collection of training documents, like a certain word might never appear in any of your training documents. And so you end up getting a word count of 0. And if you just took your raw counts and you divided by the total counts, then the probability of that word would end up being a 0. But then that causes problems. If you have a probability of 0 for the likelihood, and then that word does appear in the document, then the posterior probability for that document just becomes 0 as well, okay? Which is generally undesirable. So Laplace smoothing is basically, we just add a 1 to the numerator, so you'll never get a 0, and then we add 2 to the denominator, so that you also don't run into the opposite problem where you have a proportion of 1, okay? So we just kind of basically just blend in, a 1/2 somewhere in there, okay? And then the other part is, because we're multiplying a whole bunch of small probabilities together, sometimes we run into the limits of floating point numbers, and so you get like numeric underflow, because I don't know, whatever the limit is for our floating point numbers, it's a small number, but it's also, you can run into these limits. So a lot of times we deal with log probabilities instead, and that just kind of helps stabilize our estimates. Okay, let me give you your first view quiz answer, which is the letter D. D as in dog. Okay, here is another example, and this is, I don't know if it's not really that real, just because there's all kinds of like patient privacy practical issues, but it can be used in certain cases. We can use a naive-based classifier to perform some kind of diagnosis, some kind of classification here, okay? And so here we're gonna say we wanna take some data and try to predict if the patient has the flu, a cold, or allergies based on their symptoms. And so our training data, might consist of some patient listings along with their symptoms and their diagnosis, okay? And so here is just a fictional data set. And so we have fever, cough, nasal congestion, body aches, fatigue, and sneezing. And we'll put this together into our fictional data set, okay? So this, individual one, they had fever and cough, body aches and fatigue, and their diagnosis was flu, right? And then this person had fever, cough, nasal congestion, and sneezing, but no body aches, no fatigue. They had a cold. This person had no fever, no cough, nasal congestion, no body aches, no fatigues, but sneezing, and we'll say that was allergies, okay? And so on and so forth. We got data kind of filling this out, and so each one is kind of like, if they had that symptom, it's a 1. If they don't have that symptom, it's a 0. And then, what was the diagnosis? So this is going to be our training data, and we will train our model based on this, and and then when a new case comes in, we'll use the naive-based classifier, okay? And so, again, with the naive-based classifier, we are not going to worry about the covariances between these different symptoms, okay? Clearly, certain symptoms are more likely to appear together than other symptoms, right? Like if you have body aches, you're more likely to also experience fatigue and things like that, right? So certain symptoms certainly are going to be more likely, but then how much data do you need to fully be able to estimate accurate covariances, okay? And that's a challenge, okay? And that's a challenge. And so the naive-based classifier says, you know what, let's not worry about the covariances, okay? Because if we wanted to do the covariances, then you need to have how many? 1, 2, 3, 4, 5, 6. So what is that? 6 choose 2 is 15. Okay, you have 15 covariance terms, and so you would need 15. You have 15 covariance terms, 6 variance terms, 6 means. So you need at least 6 plus 6 plus 15. I don't know, what is that? 27. So you need at least 28. Like that. That's going to use up 27 degrees of freedom right there. Just trying to estimate each of those things. So you need lots of data, and it's going to be hard to get accurate estimates for each of these things. So again, naive Bayes classifier, we're not going to worry about it. Okay, so we'll do the full thing. We'll calculate our prior probabilities. We'll do our likelihoods, and then we'll get our marginals and posteriors. Okay, so for prior probabilities, we'll just say, all right, in our training data, flu appeared. We have 20 patients. Flu appeared 7 times, so we'll assume 35% chance of flu. Cold appeared 7 times, so 35% chance of cold. Allergies appeared 6 times, so 30% chance of allergies. This is a huge assumption that our training day is representative of the patients that we'll see in the future. But anyway, this will be our prior probabilities. Okay. And so as far as prior probabilities in R go, we'll just use our table function, and that will just give us counts, and that will give us 6 for allergy, 7 for cold, 7 for flu, and then I'm going to divide by the number of patients, and so I get those numbers. Allergy has a prior probability of 0.3, cold prior of 0.35, and flu for prior probability of 0.35. Okay, and then and now to calculate our likelihoods, we're going, the likelihood is basically what is the probability of your data given a certain class. So for example, I might want to know what is the probability of experiencing fever if you have a cold. Okay, so I could filter my data to just diagnosis as cold, and I could say, okay, how many patients experienced fever? And so we say, all right, well, 2 patients experienced fever, 5 did not. So our raw value would be 2 out of 7. Okay, but again, with Laplace smoothing, just so for example, with our cold, we had 100% of people experienced sneezing, and so if we use this as our training value, that means if somebody did not experience sneezing, then there's based on our training data, they would have a 0% chance of having a cold, which probably isn't correct. Okay, and likewise, if something had a 0, okay, if our sum was 0, then we would run into kind of the opposite problem. So anyway, with Laplace smoothing, we're going to add a 1 to the numerator and a 2 to the denominator to avoid 0 probabilities and 1 probabilities. So in our case, we had 2 people experience fever, so we're going to just add 1 to the numerator and get a 3. Out of 7 patients total, we'll divide by, add 2 to that, we'll divide by 9, so 3 out of 9. So our smoothed value is going to be 0.333. Okay, and we'll do this for every single diagnosis and every single symptom. Okay, and so I can do this very easily with something like dplyr. I'm going to just group by diagnosis, and then I will just basically do a sum or a count. I guess a sum of, because we have zeros and ones there, so we're going to just do the sum of each of these things. And so so this is what we have. This is our counts. The n over here is how many patients who had that symptom. And then so these are the counts, and basically on the next slide, I'm going to take each of these counts, and I will add 1 to each of them, and then I will divide by, and I'm going to add 2 to the n. Okay, so I'm going to just do that for each row. So we'll have allergies, we'll add 1 to the numerator and 2 to the denominator, so we'll have basically 1 over 8, okay? And then over here, all 6 people had nasal congestion, so we'll add a 1 to the numerator, we'll do 7 divided by 8, and we get 0.875 and so on and so forth, okay? Similar thing for the cold. We had 2 people with fever out of 7, so we'll add 1. We saw that calculation. We get 0.33. And similar stuff, as far as the flu, all 7 people had fevers. We'll add 1 to the numerator and 2 to the denominator, so we'll have 8 over 9, and we'll get this. Okay, so these are all of our likelihoods. This is, if you have this diagnosis, what is the probability that you will experience this symptom, right? So it's the probability of the symptom given the diagnosis, and so we have all of these values here, okay? And so let's say we have a test case where a person comes in and they say, I have fever, I have a cough, I don't have nasal congestion, I don't have body aches, I do feel fatigue, but I'm not sneezing, okay? So based on these symptoms, can we give a probabilistic estimate for what is their diagnosis, okay? So what we have to do is we'll kind of, we look at this table of likelihoods, and if we were to do this manually, right? So this patient, we had fever, had cough, no nasal congestion, no body aches, had fatigue, no sneezing, we would look it up. So let's say if we wanted to do the calculations for flu, we would do fever, 0.889, okay? Cough, the probability for cough is going to be times 0.667. They don't have nasal congestion, so we're going to do 1 minus the probability of nasal congestion, okay? They don't have body aches, so we're going to do 1 minus the probability of body aches. They do have fatigue, so we'll do that, multiply by 0.889. They don't have sneezing, so we're going to do 1 minus this, okay? Does that make sense as far as getting the likelihood for the likelihood of this sequence of data or sequence of symptoms given that they, if we assumed they had flu, okay? And so you do that multiplication and you get this number, 0.104. And that would be our likelihood of our symptoms given if we assumed they had flu, okay? And we can do that for any of the other diagnoses as well, okay? And so, this is kind of a pain to do manually. So here I wrote just a little loop, okay? And so our symptom names, we have the symptom names here, fever, cold, nasal congestion, etc. And we're going to say for each symptom, what I want you to do is I say, go to the likelihoods table, and we'll just do it for the flu. We're going to filter to just diagnosis is flu, and we're going to select the column with P of the symptom, because that's what we call these things, the probability of each symptom here, okay? And we'll pull that value. And then the symptom value is going to be these 1s or 0s. And so I'm going to start off with a score of 1, and then I'm going to multiply it by these probabilities. So we're going to multiply. If the symptom value is 1, we will take the symptom likelihood. And if the symptom value is not 1, meaning it's a 0, we're going to multiply by 1 minus the symptom likelihood, okay? And so if we run this loop, we get the exact same value that we got on this slide, okay? So on this slide, we got 0.10405, and here we get, when we ask R to do it, we get the same value, 0.10405. Okay, and then this one was just for diagnosis flu, so I'm going to make a loop of loops, okay, nested loops, where I'm going to say, okay, now do it for flu, and then do it for cold, do it for allergies, okay? And so I'm going to do that here, and then so I say, for class and classes, our classes are going to be allergy, cold, and flu. Basically, I just copied and pasted that same exact code, but then whatever score I get, I'm going to put it into the scores vector, and this is what I have. Okay, so allergies, I have 2.6 times 10 to the minus 5. Cold, I have 1.26 times 10 to the minus 3. And then flu, I get 1.04 times 10 to the minus 1, which is exactly the same as 0.10404, okay, or 10405. So that works. This is what we have. That's our likelihoods, our loop of loop for likelihoods. And so to get our posteriors, our numerators will be our prior probabilities. So again, this is the vector of 30% for allergies, 35% for cold, 35% for flu. We'll take that, multiply that by our scores, and sum them up. And our posterior will be our numerators divided by are marginal probabilities, and therefore, if these are the symptoms coming in, fever, yes; cough, yes; no congestion, no body aches; fatigue, yes; no sneezing, we're going to say there's a 99% chance it's flu, maybe a 1% chance it's cold, and almost a 0% chance that this is allergies. Okay? So that's our posterior calculations. All right. Here's just another example where here's a new patient. They come in, no fever, no cough, yes nasal congestion, no body aches, no fatigue, yes to sneezing. Okay, and so I could do the likelihoods for their symptoms. Okay, and again, we're just taking the product of each of these things. If they don't have it, we do 1 minus this probability, and if they do have it, we do 1 times that probability. Okay, and so when we do that, these are our likelihoods, and then we'll do the marginal and our posteriors. And so in this case, if our symptoms are just nasal congestion and sneezing and no other symptoms, then the most likely diagnosis is going to be allergies of around 94%, maybe a 6% chance of cold, and almost a 0% chance of it being fever, if these are our symptoms there. Okay, and I guess that's it. That's all I have prepared for today's lecture. But yeah, these are, I guess, just some kind of 2 use cases for the naive Bayes classifier, where again, all of our calculations are simplified because we're not going to bother estimating covariances between any of these terms. And yet we still get decent performance. All right, let me give you your last 2 view quiz answers. Second one is B as in bear, and third one is D as in dog. Okay, so second answer is B, and your third answer is D. Okay, we'll go ahead and end here. Have a great weekend. Have a happy Mother's Day. Good luck as you study for the midterm exam, and we'll see you Monday. So I'll send out a seating chart and all that. So we'll see you Monday.